All right, so let's jump into it. My name is Tate Niekamp, and this is Physics 2 Lab 4. So the introduction, so the purpose of this lab is to use the principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behaviors of ohmic resistors and capacitors. So basically, I'm going to calculate fundamental constants for RC circuits and compare between parallel and series circuits. So some physics principles used are Kirchhoff's loop rule, where the sum of all electric potential differences around the loop is zero. The node rule, where at any node in an electrical circuit, the sum of the currents flowing into that node is equal to the sum of the currents flowing out of that node. And Ohm's law, V equals IR, where V is voltage, I is current, and R is resistance. So the system and the surroundings, I used the virtual circuit, the CCK software. So the system is the circuit calculated by the software. And some assumptions we have is that we assume steady state equilibrium in the circuits without a capacitor. And our main result, as you'll see throughout the rest of the lab, is that my predictions were very close to the actual observations seen in the software. So the experiment. So model 1, where we charge conservation and energy conservation in series circuits. So and below you can see that I named ammeter 1 is on top and ammeter 2 is on the bottom. With Ohm's law, I predicted that I1 and I2 would be about 0.02 amps. And from the CCK software, the readings of both ammeters is 0.02 amps, and when you insert them backwards, they read negative 0.02 amps. And this result matches my predictions. So then I replaced the ammeter 2 on the bottom with a voltmeter, and the ammeter read 0 amps because it's an open circuit. And the voltmeter read negative 3 volts due to the direction of the current and the placement of the probes, where I placed the black probe at the point of peak potential difference due to the batteries. So then we used the voltmeter to see the potential differences around the circuit, where from A to B was 3 volts, B to C was 0 volts, C to D was about negative 0.96 volts, D to E was 0, and E to F was about negative 2.04 volts, F, G, G, H, and H, A were all 0 volts, and the current I is 0.02 amps. So with Kirchhoff's loop rule, you can see that measured from A to B was 3 volts, C to D was negative 0.959, and then E to F was negative 2.041. So that all sums up to 0. So then after attaching the voltmeter, the ammeter reading does not change. This is because the voltmeter has no effect on the potential difference and it does not modify the current of the circuit. So after connecting the voltmeter across the 100 ohm resistor, the ammeter read negative 2.041. In the graph below, you can see between C and D it decreased. D to E was no increase or decrease. And then E to F, the volt decreases all the way to 0. So after replacing the voltmeter with an ammeter in parallel with the 100 ohm resistor, the ammeters are now part of the loop, including the 100 ohm resistor. So the current is then increased as the resistance decreases. So using measurements from part 5 and 6, the resistance of each of the following circuit elements is the 47 ohm resistor was 47 ohms, the 100 ohm resistor was 100, the wire was 0, and the ammeter was 0. So now jumping into model 2, the RC circuit. So with the light bulb and capacitor in series, the light bulb slowly dims over time. And after disconnecting the battery and then connecting the capacitor directly to the light bulb, the capacitor discharges, which instantaneously lights up the bulb, and then the bulb dims again over time. So in both situations, the current decreases over time. So then we had to charge or time the charge and discharge of both bulbs. So for the 10 ohm bulb, charged in 9.5 seconds and discharged in about 8.83. The 20 ohm bulb charged in about 19.84 seconds and discharged in about 15.31 seconds. Here is my graph of the natural log of delta V over delta V0, and it's linear as it should be. And so this prediction makes sense, as the RC is equal to the time where the voltage is roughly 1 over E of its original value. So this computed value agrees with the RC value of the circuit in CCK, where the RC is equal to 30 ohms times 0.2, which is about 6 seconds. And you can see my calculations below, using the formula on this slide before. So some sources of error. So since the computer is a computer program, there's little to no error in the system. However, there is a possible error in the timing of the charge and discharge times. And so jumping into the conclusion, my what if. So if this lab was done in real life, the ammeter would have a small amount of resistance, which would have decreased the total current in the circuit. For number 2, if the ideal model predicts that the capacitor would be instantly charged when connected to the battery without resistance. However, in an unideal system, there would be a delay, as it would not be able to happen instantaneously, and it would also have to face resistance from the wire, even if only in a small amount. All right,